Welcome back. This is the Tutor Wizard. What we're going to do again, like I mentioned before in the previous video in this section, is we're going to do pre-calculus final exam review problems. Let's pick up where we left off last time. In the first video we did 8 problems, so we're going to continue just numbering them from 9 to hopefully 16. We'll see how far we get. We're going to do a bunch more. This number 9 asks us sine theta is 3/7 in a right triangle, and it wants us to find the other 5 trigonometric ratios. I know, yeah. This is Jasper. She wants to check too. We're doing trigonometric ratios. You gonna be quiet or you gonna be loud like your sister? You're a good girl. She's messing with everything in the background, so I thought I'd throw her in. That's Jasper, the white devil. We're looking for the other 5 trigonometric ratios in a right triangle. The first thing you should do, if you can, is draw a right triangle for yourself. So let's do that. I have a right triangle. It tells me that what can I label? I'm going to label this the angle theta. And then what does it say? It says sine theta is 3/7, which is opposite over hypotenuse. So this tells me that if this is my angle now, this has to be a 3 and this has to be a 7, and this is our unknown value A. And we can find this. We can always, if given 2 sides in the right triangle, we can find the third using Pythagoras' theorem, which is what we're going to do right now. This says a squared plus 3 squared equals 7 squared. Solving for A and picking the positive square root, we get a squared is equal to 7 squared minus 3 squared, or a squared is 49 minus 9, which is 40. This gives a is the positive square root of 40, or a is 2√10. What do we do with this information? This says a was 2√10. And we can continue by finding all 5 trigonometric ratios. It already gave us sine of theta is 3/7. This means we can find now the other ones. Cos theta is going to be adjacent over hypotenuse, which is 2√10/7. Tangent is opposite over adjacent. So that will be 3/2√10. This also gives us the reciprocals of these. Cosecant is 1/sin, which will be 7/3. Secant will be 1/cos, which is 7/2√10. And tangent cotangent will be 1/tangent, which will be 2√10/3. These are the 6 trigonometric ratios in a right triangle. Next up, number 10 is wanting us to sketch the graph of a function y equals sine of 3 times in brackets x plus pi over 6. What we want to do with this essentially is see this as the standard function of sine x, look at its graph, and then look at some key points in its period, in one of its periods, and then we're going to copy it over and over again, and we're going to do the standard transformation it tells us. In these cases with the sinusoidal functions, we have specific names for all of these things. So let's go through them one at a time. We don't have any amplitude because there's no number on the outside, so we don't have to worry about amplitude. So amplitude is just 1. It's going to stay the same. Wave is going to be the same height from -1 to 1. What I also want to do is, depending on what they call this, I'm going to look at the period. The period of the regular sine function is 2 pi, and so the period of a function which has a value on the inside is 2 pi over 3, so because of the 3. So this tells us in general, the general sinusoidal function is y equals a sine of b x plus k plus d, depending on which ones they give you. I'm not sure which ones they put this as. They may have switched these. Possibly they may call this K and this B. The phase shift they're going to call B and K. Do you want this then? So if this is the general sinusoidal function, what we're looking for is these main four things to happen. This will be horizontal or vertical stretch and shrink, or which we call amplitude. This will be involving the period, which will be horizontal stretch and shrink. This will be phase shift, they call it, shifting left and right. And this will be vertical shift up and down. In ours, we have this guy and this guy, so we're going to have a shrunken period, compression horizontally, and we're going to have a shift left by pi over 6 units. This period being 2 pi over 3 tells me that now what we're going to do in general to get key points on the graph of sine x is we want to do the period over 4, which in this case is going to be 2 pi over 3 divided by 4, which is 1/4, which is going to be cancel and cancel. We're going to get pi over 6 conveniently. So what that means is 1, 2, 3, 4. I'm going to break my period, which is now 2 pi over 3, into 4 equal pieces, where sine is 1 and 0 and minus 1 and 0 in the regular sinusoidal function. This is my full period. This means that this was pi over 6, and then pi over 6 plus pi over 6 is 2 pi over 6, which is pi over 3. That gives me this next point. And then pi over 3 plus pi over 6. Now I have to multiply by 2, which is going to give me 3 pi over 6, which is pi over 2, this one, and then 2 pi over 3. So these are the key points that I need in this interval 1 period length of my new period for the function they gave me. Once I do that, I can deal with this first guy, which is the period or horizontal compression by a factor of 3. Then we'll shift. The two things we're going to do is 1, horizontal compression by 3, a factor of 3. What we call that is the period is going to be P is 2 pi regular and then divided by 3. And then 2, what we're going to do is phase shift, which is horizontal shift left and right by left by pi over 6 units, because we actually have minus pi over 6. Let's do the period first, and then we'll just shift it back with a different color, and then that will be our final function. What are we going to get this time? So I draw sine. Sine of 0 is 0, and then we're going from minus 1 to 1 because we didn't change our amplitude. Sine of now pi over 6, our new function is going to be sine of 3x would be 1 here, then we're going to get 0, then we're going to get negative 1, then we're going to get 1. So that is the sine function horizontally compressed or having a new period of 2 pi over 3. That is the function sine of 3x, which has shrunk the period. Now I can do the second thing that happened to this function, which is shift left pi over 6 units. So why it's convenient for me to have focused on dividing the period length in by 4 and finding those key values is now all I have to do is to go left. If it matches, which it did in this case luckily, I'm going to shift each point back pi over 6 units to give me this one's going to go here, this one's going to go here, this one's going to go here, this one is going to move here, this one is going to move here, and we are going to get our final result, which is y equals sine of x plus pi over 6. Sketching sinusoidal functions. Next question. Okay, and number 11 is similar to one that we did in the first Precalculus final review video, which is finding equations of lines in the plane. This time they gave us 2 points on the line, and they're saying find an equation of this line. It also often quite helps to just draw a picture for ourselves. This is not the scale, but we're going to pretend if this is the point P and this is the point Q, what we're looking for is the slope first is what we need. So we're going to do rise over run, which is change in y over change in x. And so we need the slope, which is going to be exactly this, the change in y over the change in x, or rise over run. Once I do that, now I can put the values in there. What was that? That's going to be, again, this point, the y2 and the x2 and the x1 and the y1. They tell us y2 minus y1, so that will be -2 minus 1 over, now what are we going to get? x2, 3 minus 1, which is going to give me -3 over 2, which gives me the slope. Once I have the slope, all I need is a point and the slope, and I can create the point-slope form of the line. So let's do that. This is going to give me y minus 1 equals -3 over 2x minus 1. This is the point-slope form of the line. If you really want to clean it up, or they ask for the slope-intercept form, or you like it more like that, this will be y equals -3 over 2x plus 3 over 2 plus 1. I'm moving this over also, and this is going to give me common denominator 2 over 2 is what I multiply by. So this gives me y equals -3 over 2x plus 5 over 2. This is the slope-intercept form of the line. Or number 12 wants us to find the exact value of cos of 8 pi over 3. So what they're saying in these questions usually is finding the exact trigonometric values of arbitrarily large angles or values. What we want to do with this is first cut off any excess revolutions of this value to find value on the unit circle, or between 0 and 2 pi, which is coterminal to this value, 8 pi over 3. What I do with this is first I call the angle alpha, which is 8 pi over 3. The first thing we want to do is cut off excess revolution so I can find an angle theta, which is coterminal to alpha, which means that they'll have the same trigonometric ratios and the exact values, but theta will now be on the unit circle, and you can use the unit circle and the cast rule or whatever we're going to use, I'll show you in a second, to calculate the exact value of this. So step 1 is from alpha, the arbitrarily large angle they gave us, we want to compute an angle theta between 0 and 2 pi. How do I do that? I cut off excess revolution, so I'm just going to subtract 2 pi from this. Alpha minus 2 pi is 8 pi over 3 minus 2 pi. I need a common denominator, so I multiply by 3 over 3. This gives me 8 minus 6, which is 2 pi over 3. This gave me, now if I cut off one excess revolution, what that says is the angle alpha they gave me is actually coterminal to 2 pi over 3. What alpha did was it started here and it went all the way around and then it stopped there. And so alpha is coterminal to theta, which is now theta is between, which is 2 pi over 3, is between 0 and 2 pi. I'm on the unit circle essentially now, is what I wanted. So step 1, cut off excess revolutions of the angle. Given alpha equals 8 pi over 3, cutting off excess revolutions gives us coterminal. 0 is less than or equal to theta, which is 2 pi over 3, which is less than or equal to 2 pi. It's on the unit circle. Step 1, cut off excess revolutions. That 8 looks weird. Let's draw that again. 8 pi over 3. Now what are we going to do? Step 2. From this, find out what quadrant you're in and find the sign using the cast rule of your trigonometric ratio. We just saw that 2 pi over 3, or 120 degrees, is in quadrant 2. This is 1, 2, 3, 4. Once I know that, that tells me by the cast rule or whatever you're using, C-A-S-T, that cos is going to be negative. What I like is plus plus, minus plus, minus minus, and plus minus. This is how we're going to go around. In this quadrant, cos is negative and sine is positive is what that tells me. This gives me that cos of 2 pi over 3 is less than 0, so we're going to, the sign is negative, we're going to get a negative is what we're going to keep. And then finally, I need step 3, find the reference angle, theta bar. Theta bar is dependent on, it's the acute angle formed by the terminal side of ray of your angle in standard position and the x-axis. So in this case, in quadrant 2, this would be theta bar, and in that case, that is going to be pi minus our angle. So theta bar is pi minus 2 pi over 3, which is going to be 3 pi over 3 minus 2 pi over 3, which is pi over 3. So our reference angle is pi over 3. We know what sine it is going to be, and then I piece it all together. Step 1, cut off excess revolutions. Step 2, find out what quadrant you're in and the sign of your trigonometric ratio or angle exact value. And then step 3, find the reference angle dependent on which quadrant you're on or in. We put that all together, and what does it give me? This says that cos of 8 pi over 3 is equal to cos of 2 pi over 3 because they're coterminal. And then this is times the sine of cos dependent on your angle and times cos of the reference angle. What was that? In our case, the sine of our trig function was going to be negative because cos is negative in that quadrant, and our reference angle, where are you going? Our reference angle was pi over 3. And this gives me negative, what's cos of pi over 3? 1/2, that's correct. We're essentially reducing ourselves to knowing what the sine of the trig value is and the reference angle. Once we cut off excess revolutions and then find the reference angle, this allows me to memorize first quadrant unit circle values and the sine. This is how we find exact values of cos of 8 pi over 3. Or number 13. 13 wants us to sketch the graph of function g of x from a standard function and using transformations. In this case, it's a quadratic, so what are we going to have to do? Complete the square. Complete the square. First of all, let's go through that for a second. Why do they call it complete the square? Say I have this, and let's say this side is x, so this side is x. This is going to be b over 2 and b over 2. This side is x, and this is b over 2. Let's label everybody b over 2, x. Now, what's the area of this square? It's x times x, because that's the side, so x squared. What's the area of this rectangle? X times b over 2. What's the area of this rectangle? It's also the same, x times b over 2, length times width. X times b over 2. When I add those two things, I'm going to get bx. So x squared algebraically represents the area of this square, why we called it x squared, plus bx represents the area of these two rectangles. And what would I need to complete this square, which would be the total area of what? What's the side of this? X plus b over 2 times x plus b over 2, or x plus b over 2 squared. What do I need to complete that square? I need b over 2 times b over 2, or b over 2 squared is what I need to complete the square. The little piece that comes in there is that's what bothers you. This tells you what you need, but you can't just add that in the formula. That's crazy. We're going to add 0 in the form of b squared over 4 minus b squared over 4, and then it won't change it. Here we go. G of x equals 3x squared minus 5x. The first rule of completing a square is get the x by itself. So I need to factor 3 out of both. And you're like, there isn't a 3 here. Yes, there is. I just multiply by 1. Now I'm going to factor this 3 out and this 3 out. This gives me 3 times x squared minus 5 over 3x. Now what do? This is the b. What do I need to complete that square? I need b over 2 squared. So b over 2 is equal to negative 5 over 3 times 1/2, which is negative 5 over 6. B over 2 squared is 25 over 36. Once I have that, what do I need to complete the square? To complete the square, I need b over 2 squared. So b is equal to negative 5 over 3 over 2 is times 1/2, which is negative 5 over 6. So b over 2 squared is this squared, negative 5 over 6 squared, which is 5 squared, 25 over 36. What are we going to do? We're going to add that, but we're going to add it in 0 as 25 over 36 minus 25 over 36 equals 3 times inside the brackets, negative 5 over 3x plus 25 over 36 minus 25 over 36. This is now the completed square, what I wanted, but I've added 0, so I didn't change anything. Equals 3 times x minus 5 over 6 b over 2, all squared, minus 25 over 36. Finally, be careful, this 3 distributes onto everything, and we will get what this shift is. This gives us equals 3x minus 5 over 6 squared minus 25 over, we cancel a 3 in there, we're going to get 12. 3 over 36 is 112. So this is g of x. I can't tell what the transformations are in this form, but once I complete the square and put it in standard form, I see that we have vertical stretch by 3, then shift left or right 5 over 6 units, and down 25 over 12 units. Let's do that. Our standard function was this guy, g of x equals 3x squared minus 5x. We completed the square to put it in the standard form. Now I can see 1, we have vertical stretch by 3. 2, we have shift horizontally right by 5 over 6 units. And 3, shift up and down, particularly down 25 over 12 units. To do that, the original function f of x is x squared. Our standard function starting with is x squared. If we vertically stretch that at 1, it will grow by a factor of 3. So this is the vertical stretching of 3x squared. Then what are we going to have? Let's shift that right 5 over 6 units. So I just mark 5 over 6 units. And we shift that to the right. This will be 3 times x minus 5 over 6 squared. And then finally we have to shift it down 25 over 12 units. We just mark it as negative 25 over 12, and our new vertex is going to go here. This is our function g of x, which was 3x squared minus 5x. Standard transformations of functions. More. All right, number 14, what we're going to do is we're going to do more completion of squares. So just like in number 13 when we were doing the standard transformations of g and we had to put it in standard form and complete the square, now we get to do it on 2 variables, x and y. Yay! Before we start that, in your mind what you want to see is, I am told that they give us this formula. And if this is the standard form of the equation of a circle, and what that tells me is the center is HK, hunter killers HK, that's something different. And then the radius is R. So remember, usually when we get the final result, it's not 5. If this is the final answer, it's square root of 5 would be the radius. R squared is, so it says R is the radius. Ours doesn't look like that. If you look in the standard form, what hopefully I'm seeing, and then what you're going to now see, what you weren't seeing, is this one has an x term and a y term. This form doesn't. And luckily we're going to use Francois Viette from the 1500s, and he's the first one to complete the square. So just like in the last one, we're going to complete the square here and complete the square here, and it's going to get rid of those middle terms so it'll look like this. Then when it looks like this, I can decide whether what the center is and what the radius is. Here we go. The first thing we do is I group them together. Essentially all I'm doing is putting brackets around them to make myself feel a little bit better. You can do that too. Once I've done that, I have to complete the square of this variable and complete the square of this variable. For this one, b is -3. Or sorry, -6. I was jumping the gun. I was trying to divide in my head. Brain was doing something other than the mouth. b is -6 over 2. is negative 3. So b over 2 squared is 9. I need a 9. But remember from the last one, I can't just add 9. That's crazy. We're going to add my favorite dirty trick, 9 minus a 9. For the y's, I have b is 4. So over 2 is 2. So b over 2 squared is 2 squared, which is 4. But I can't just add 4. I'm going to add 4 minus 4. This gives me x squared minus 6x plus 9 minus 9. I've added 0 into that first bracket. And then plus y squared plus 4y plus 4 minus 4. I've added this 0 in there. Equals 5. What did that do for me? These are the completed squares now. So that gives me, this is x minus 3 squared minus 9 plus y plus 2 squared minus 4 equals 5. Now what we're going to do is group all of these numbers together and move them to one side. So I have x minus h, y minus k equals r squared. Now that we have that, basically I just brought the numbers to the other side. I grouped them together. I get 18. Let's write that one more time to show you what I'm seeing now. I see this. This is the x minus h squared plus y minus 2 is plus 2. K squared equals r squared. This is 18 is the square root of 18 squared. This is a dirty little trick I remind myself of. This says that the center is HK, which in our case is the center is 3 and then minus 2. So negative 2 is my center. And the radius is the square root of 18, not 18. Give me more. 15. For number 15, what they want is for us to decide if a function is even, odd, or neither. So the definition of even is you're even if f of negative x equals f of x. You're odd if f of negative x equals negative f of x. And you're neither if you're not even or odd. Not every function has symmetry, and these tell us something about symmetry also. If you're even, you're symmetric with respect to the y-axis. X squared is an even function. And if you're odd, you're symmetric with respect to the origin, they say, or if you reflect about both axes, you will get symmetry. That's x cubed is symmetric. Even powers, odd powers. This is why we call it even odd. What are we going to do therefore? We're going to put negative x where x was. F of negative x is negative x to the 4 minus 2 times negative x squared plus the absolute value of negative x. In the first one, the even power kills the negative, so x to the 4 minus 2 times x squared kills the negative inside the brackets, and plus absolute value kills this. The absolute value of a is equal to the absolute value of negative a. So this is the absolute value of x. What is that? F. So f is even in this case. Let's do one more. This function, f of x, is x to the 5 minus x to the 4 plus 3x squared plus x. This is going to be neither even nor odd, and this is a little bit harder to check, but I can tell sort of when I start if it's just polynomials. If it has even and odd powers, some are going to spit out the negatives, some are going to eat them, so it's not going to be f of x or negative f of x. F of negative x is negative x to the 5 minus negative x to the 4 plus 3 times negative x squared plus negative x. In the first one it spits it out, so I get negative x to the 5 minus, this one will eat that negative x to the 4 plus 3. This x squared will eat the negative x squared, and then minus x. I look at this. This is not f of x, and it's not negative f of x either, and it's hard for you to see this at first, but this is f of x. If you look at it for a second, f of x has one negative term and 3 positives. And then if I was going to hit negative f of x, what would that look like? It would look like negative x to the 5 plus x to the 4 minus 3x squared minus x. But if you look at where the negatives are, this is definitely not negative f of x, and it is definitely not f of x, because it doesn't match in both cases. So this is neither even nor odd. One more. 16. Let's do one more, and then this will be the end of video 2 for pre-calculus final exam review questions. There will be one more. I'll crush out a whole bunch more problems about pre-calculus and what you may or may not see on a final exam. Most likely, hopefully, you will see, but they can't pick all of these, obviously. So they're going to pick some from these categories of types, styles of questions they're going to give you. Solving inequalities. Absolute value inequalities also bother everyone, so let's close off with this. Solve the absolute value inequality. 7x plus 3 is strictly larger than 5. What we do with this is, it says if a of x is larger than c, where c is positive, this is if and only if a of x is larger than c. So first, just strip off the absolute value. That's how you do that, remember that. Or a of x has to be less than negative c. What did they give us? This is our a of x, 7x plus 3, and this is our c, 5. So I'm just going to run that with our definition. 7x plus 3 is larger than 5 if and only if 7x plus 3 is larger than 5, or 7x plus 3 is less than negative 5. That's the first step. Now the absolute value bars are gone. Now we solve these two inequalities for x. Let's subtract 3 from both sides. This gives me if and only if 7x is larger than 2, bringing the 3 to the other side, and I'm bringing the 3 to the other side, or 7x is less than negative 8. In the final step, 7 is positive, so when we divide by 7 or multiply by 1/7, this is also positive, so it won't change the inequality, and this gives us x is larger than 2 over 7, or x is less than negative 8 over 7. As an interval, what does that give us? X is inside negative infinity, negative 8 over 7, union 2 over 7, infinity. This is where this is true, is in these two intervals. Subscribe below, hit the notification bell, and you'll get many more of these videos when we post them. Thanks, and I'll see you next time for part 3. Okay, bye. That was the camera guy, so apparently I'm doing this by myself. Shh.